Okay. Hi everyone. Today I will happy to share with you is a segmentation, location, localization, and the detection. So begin that. Last few lecture we are learning about CNN. So when we begin this lecture, we just do some works for CNN. So for CNN works, the input is an image, right? And we have several layers. We're doing convolution and pooling and during this process, after a fully connected layer, what the output for the picture is, we can output for the whole picture, 90% is kept. So for CNN network, the problem to solve is we input the picture and output what kind of possibility this image stands for. But in real world, there are many other application image processing problem we need to solve. Here's a 4 problem. One is segmentation, one localization, detection, and segmentation. So for this one, first of all, I will share with you the segmentation problem. So what the problem is, the input is one picture, the same picture, but the output is not show what the possibility of this picture is. The output for this problem is we need to split the whole picture and tell the user, okay, in this picture we can split into 4 parts. It consists of glass and cat and a tree and sky. So the problem change a lot. So when we're doing this problem, we have some definition. So what's our purpose for the segmentation? So when we input one picture, we need to output and split all the parts of the picture and indicate which one is sky, which one is tree, which one is cat, and which one is glasses. And one more thing I need to highlight here is we just need to find out what kind of the things this area is. We do not say how many numbers of this object. For instance, we have 2 calls here, but in this problem we just recognize, okay, this 2 calls area is call. We do not say, okay, there are 2 calls. So this is a problem we want to solve. To solve this problem, one very straightforward thing, manner we maybe first coming in our mind is we can just, right now we just have CNN network. We can just split all the whole picture into small pieces, and for each pieces, we just use the CNN network to say, okay, this area is what. For instance, we have 3 pieces of picture, and we put the first picture here, and in the CNN, we say, this is a call, and this part is call, this part is grass. So this is a very straightforward manner of how to solve that problem. But the problem, if we do like this, it's very ineffective because we do not know how we cannot reusing the shared feature between overlapping features such as this area. Another way to solve this problem is we can figure the whole, treat the whole picture as a whole, and we label each part of the area into the original picture. For instance, for the training data set, we have such kind of the picture. What we should do is we do not just mention, okay, this is a call. We need to, instead of that, we need to mention, okay, in this picture we have 2 calls in this area, and we have sky in this area. This is glasses in this area. This is a tree. So after that, we just need to have a training set. We just need to do in the several convolution layer. Then finally we can get what kind of picture, what area of the picture it is. So it can solve the problem. But if we do like this, the problem is for the training data set, it's very expensive. Just as I described before, we for the training data set, we need to label every part of the image and figure out what kind of things it is. So the training data set it's very hard and it's very expensive to get such kind of a training data set. So to solve such kind of a problem, right now we propose to use this downsampling and upsampling method to solve this problem. And then I will show you what is downsampling, upsampling. As I understood, in general, what this kind of things do is, first of all, we use downsampling to get some feature of this picture. And so after this process, we can get the different part of features. So we call it downsampling. And after that, we use upsampling. We use some other function to pulling the features to the whole picture, then split the whole picture to several areas. So here's some pulling function. We give some example. For instance, after the down pulling section, we get the picture. Okay, it consists of one cat. It consists of cat, glasses, tree, and sky. So we get 4 features: 1, 2, 3, 4, and we can just putting into 1, 2, 3, 4. Just split the whole picture into 4 parts. And another function we can do this is we just use 1, 2, 3, 4 in the part of the matrix and makes 0. Filling up the whole matrix. And another uppulling method is max uppulling, which is a very classic. So the method we use here is for the downpulling session, we will get the max feature in this matrix. Here is 5, 6, 7, 8, and so we can see this is a feature of this part of the image. So we do it after doing the downpulling session. We just get a feature 5, 6, 7, 8, and it will after the rest of the networks it will stand for maybe 1 stands for sky, 2 stands for tree, 3 stands for the cat, and 4 stands for the glasses. So after that we do in max pulling session is we need to remember where is the max feature, the location, and we use this 1, 2, 3, 4 replace the max pulling position. And another way to doing the upsampling is transporting convolution. Here's an example. This is just like a common convolution. We just say the strap equals to 1, pair equals to 1, and the kernel is 3 plus 3. And so we move the kernel and we can calculate the output. Here, if we want to squeeze the image and get the feature, we can say the strap is 2 and pair is 1, and the process is when we move the kernel, we calculate and get the output. For uppulling session there's a little bit different. When we consider the uppulling session, here is a little bit different because we can fill up this area, but in this area we need to put it in somewhere output overlaps. Later we have an example to show what it works.
All right, my name is Xiaoming. I graduated from NUS quite a few years ago. So next, I'm just going to run through with you the example of this transpose convolution. All right. So over here, you view it as a 1D example. It's actually easier to explain. So transpose convolution, we are actually getting a feature map. We want to actually map it to higher resolution. Over on the left side, we have the input, which is 2 pixels, and we're not making it to 6 pixels, sorry. And then we have the filter. And then we can see a convolution or strike 2 convolution, strike 2 transpose convolution. So the window will be here, and the strike 2 will be here, and then this overlapping part, so there will be sums over here. And then all the convolution, for convolution and transpose convolution can be represented using a matrix. All right. So this is a normal convolution that we have seen a few lectures ago. So this we can represent it using a matrix multiplication in this way. And then for transpose, we can also represent it in the matrix convolution. So the filter, this actually represents the filter positions. And then this is the transpose of the filter. We represent it this way. For this, I think if I draw out, it'll be easier. Remember that so this is our input, which is B, C, and D. All right. And then our filter is X, Y, and Z. Anyway, this one has hypo here. This one should be Z. All the 4 positions here. So over here, you have a filter, which is have a X, Y, and Z. All right. So you can pad it with 0 in front and behind. And what this does is that you are doing a convolution with a strike 1. So you can see that this to the right side by 1 position, 1 position, 1 position. This is what represented in here. So X, Y, Z, the next position, the next position. And when you do this will be your output of the convolution. And similarly for transpose convolution for strike 1, it can be represented using this kind of operation as well. So same thing again, you have A, B, C, and D. But your filter this time around will be Z, Y, and X. There are 2 0 present in front. So if you're actually doing this strike 1, move to the right, and convert each pixel by each pixel, you will get this. So that's what it means here, that for strike 1 convolution and transpose convolution, they're actually doing the same operation. But just that you have different padding and different position of the filter. But for strike 2, it will be a bit different. Okay, so again, this is a strike. This is a normal convolution that we have seen a few lectures ago, and we strike 2. So they can represent it in this. And this, you might find this quite familiar, which is the example we are using in the graphical example over here. The output is exactly the right over here. So you do this matrix multiplication, the xt, which is the transpose this matrix, you will get this output. But the thing is that in no longer a normal convolution, you will not be able to use this convolution kind of graphical method to represent this thing. You only can use matrix multiplication. For example, the first one, we are just doing normal convolution with a filter of X, Y, and Z. Yes. With a strike 2, you will get exactly what is given here. But for this one, I just simply cannot represent it using a graphical way to do it. But I cannot find a convolution filter that with a strike 2 can actually represent this. So that's why for this case, we only do matrix multiplication to get the results. Okay, just now center.
Practical implication to that? Is there a reason why you would use the method on the right side? Because you said everything can be represented with the normal matrix multiplication.
Yes. Yeah, everything can be represented in matrix multiplication. So the underlyingly just do matrix multiplication. You can do both transpose convolution. But it's just that what I try to explain what is mean here is that for this strike 2 transpose convolution, there's not a way that you can represent it in the normal convolution that you can imagine. The normal convolution, you're putting a filter onto the image, and then you move it across, then you multiply to the inner product, and that's you to get your final map, final feature map. But in this way, you're not doing that. You can just do multiplication, use a filter, transpose it, and do multiplication. You get this thing. Okay, so what we have talked about so far, unpooling, max unpooling, stranded transpose convolution, they are all the upsampling method. So the pooling and stranded convolution are downsampling method. So Spencer has mentioned that why do we need to do this is because it's very expensive to keep the same resolution when we process it. Because like in this image, there are factors that we can learn and represented in the lower resolution. So the first part we're doing this is you learn the features represented in the lower dimensional space. But you want to represent your final result in a full resolution like this. In the whole map, which pixel belong to which class. So over here, the blue part is where you do upsampling. The max unpooling, the transpose convolution, you recover the result based on this. So remember that the filter in the transpose convolution also learnable. So use the training method propagation. You will learn the filter to do transpose convolution, and all the pooling layers and all that. Yeah, and that's the part that does semantic segmentation. Okay, so next we'll be moving on to another problem, which is classification and localization. Classification is nothing fanciful. We've been through a few lectures. It to actually classify this image as what object in it, whether it's a cat, car, something else. But we have one more thing that we need to do now is localization, which is to find out what is the position of the object of interest. Okay. So one difference between the localization and the detection is that before you do the problem, you exactly know that there will be one class you want to identify. So you'll be identifying the bounding box. In this case, our object of interest is a cat. I'll be learn a bounding. I'll ask the neural network to learn the bounding box drawn around the object of interest. And then that's what I want to do. I want to identify it as a cat. I want to know where the cat is by drawing a bounding box over. Okay. So this is very similar to the classification problem that we have been through. So it's nothing fanciful again. At the front, we can still use the technology that we use for classification problem. What is shown here is LXNet. Okay. So if you look at the top parts, this is exactly what we done in the last few lectures. Using a somax function, find out the probability of each classes and pick the highest one as your target class. But over here, we're going to do localization. So we will have another layer, which and then it's a 4-dimension. It predict the four coordinates x, y, w, and h, which are the 4 corners of the bounding box. All right. So over here, you want to output this predicted coordinate of the bounding box, and then this is continuous variable. And also for this x, y, w, and h, the continuous variable, you need to use some regression loss function to represent the loss. It can be L2 loss, Euclidean loss, it can be L1 loss, something like that. And over here, again, you have the cross entropy loss. So for these two, we need to combine them together to get a multi-class loss, and then use this loss to train it, try to optimize this loss, and then adjust the filter weight based on that. Actually, there's I think this projection is cropped somewhere. There's something more here. I think you can see your slides better. Anyway, because these two functions need to be combined together. So usually there's a weight parameter between your cross entropy loss and your L2 loss. So maybe it could be something like 0.1. You put 10% weight on the regression loss. You put 90% weight on the cross entropy loss. This is a hyperparameter that you have to tune when you have to cross-validate when you are doing training. Okay. Yep. Yes. I think my student just said the LXNet you can pre-train from elsewhere. So one trick is that you can pre-train this from elsewhere, then you adjust it to your data set, and you adjust and you learn these 2 layers. One of the tricks doing this. Okay, so based on this idea, one of the example will be to do one of the application will be to estimate a human pose. So in this graph, we are trying to the algorithm trying to actually find out where the human joint is in order to deduce the posture of the human, whether it's playing on tennis or sitting or sleeping or that sort of things. So over here we said that there are 14 joint positions, and by learning the position of the joints through a lot of training images, you can actually predict. You can actually find out where are the joints in this picture. So same thing. The position of the joint is a continuous variable. So you will be predicting the 14 set of coordinates over here. All right. And then use a regression loss, whether it's L1 loss, L2 loss, something like that, to do training. Yep. So all these loss for the joints need to be added together to get a final loss. And this final loss will be used for your back propagation for your optimization. Okay, and that's all for the classification and localization.
So, before the
Previous page, okay.
So, in this case, so tutoring and neural network, so like the human need to like set the level of like let's say left foot has like a coordinate x1 and y1, so which is the human like manually set this.
Oh. Yes, for training images, yes, you might have some ground truth to say that, oh, this joint, what coordinate is that? This joint, what coordinate is that? So when you're training, that's why you will get the regression loss. How far am I from the ground truth coordinates? Then that's actually a loss function, and you optimize based on that. So yes, I mean for the training, actually for this problem, for the training images, yes, you need to have the joint locations. But even for the localization problem, for the training images, you need to have the bounding box coordinate as well. Yeah, but that's why the ImageNet set up. They all have this kind of information for you. I don't know how to do it. Maybe they ask you to actually draw a bounding box, but there are data out there to label train using these bounding box coordinates, human joint coordinate out there. Okay, so next I will pass on to Daniel to walk us through the object detection parts.
Okay, object detection. I've got some problem here. I think this doesn't belong here because you notice that here there are 4 categories. That means somehow or other they managed to implement multiple classification on this picture, but not on this picture. So I don't think that goes there. That's segmentation. But anyway, we are more interested in object detection now. We've gone through before. This actually detects, okay, and then there is a bounding box around the single object. But you can't only have one object sometimes. Sometimes you want to detect multiple objects. In this case, you need to be able to draw you need to identify the class, and identify the class has nothing to do with localization, which is figuring out where the box is. And then in this case, there's 2 dogs and a cat. And this is an example of instant segmentation. It means that not only can you get to draw the box, you actually know where all the hair or fur is. Okay. Okay, object detection has progressed quite a lot with deep learning. Previously, with traditional algorithms, I think, right, before deep concepts, yeah, you get up to about 40% maximum. But with the advent of deep learning, it's gone up to 80%. And I think 80% is not quite it because I've got figures that in 2015, they already hit about 96.53%. And in 2017, this year, they already exceeded human recognition, which I guess is over 100%. So deep learning has given us a lot of opportunities in this area, but and object detection has, I guess, improved greatly. Okay, object detection as regression. The meaning of regression is to reduce something into a set of numbers. So we've already discussed that we get from this particular picture, we intend to get this set of numbers. But whatever algorithm is, there must be the ability also to get, in this case, there's two dogs and a cat. That means total wise you got 4 times 3. This is 4 times 1. And in this sense, you cannot, I mean, the point is, object detection cannot be based on just a certain single output. You need to be able to parse the picture and then break it into its constituent parts. Each image needs a different number of outputs, which is what I was saying just now. So this case by itself really hints, but we all know that this CNN only runs through once and gives you a single set of output. So the question is, how do you get this, which only allows you to run once through it, to output different numbers of an unknown number of numbers that describe what are the objects detected within the image. Well, let's just see how we can do it using brute force method. The brute force method in this case is the sliding window method, which I believe Xavier has already. I think we already brought up this issue already. You just slide the window from one side to the other side and find out where the maxima are. So having slide the window over the dog, is detected the dog. Okay, dog, another dog, detected the cat. And after that, we did. This is the, okay. I think I saw this something, but anyway, sliding window is tedious. It takes up a lot of computational space. It probably takes up a lot of, because of taking up the computation. So the idea around it is to have something called a region proposal. Region proposal is an algorithm. Okay, it's an algorithm by itself that goes into an image that actually suggests areas of interest, ROI. Okay, the regions of interest are based on an algorithm that is not actually part of CNN. It's actually part of what you call a traditional algorithm. In this case, it is known as selective search. Then, after, I guess RCNN is the first development of a multi-object detector. Okay, so what we have just now is something called the regional proposal. The region proposal will actually flag out areas on the input image where you can probably find things, parts that you can recognize. And what the system does is take these parts, right? These regions of interest, and walk them into images that can fit, because the convolution that requires a fixed size image. So these different size regions of interest need to be walked to a standard size, which is 227, 227 in the case of RCNN. Now, all this is happening in the loop, right? So what they probably do is they probably have all those RCNNs, all those regions of interest of the image, which is output of the other algorithm, and then you follow each of them, you walk them, and then you send them through the convolution net. So in this case, you have 2,000 regions of interest. That means you need to push each one, walk each one, and send it to a convolution net 2,000 times. Then after the convolution net, then you get enough information to be able to figure out what class they came from. But that is only classification. You still need your bounding box, which for localization. So the output of the convolution net, SEM, as well as the bounding box regressor. Okay. Questions? No questions. Oh, no questions. Okay. RCNN obviously have a few problems, right? Firstly, you have your region of interest detection, which is separate algorithm, not even here. Okay, and all these ROIs magically appear. No, it's actually calculated by a separate algorithm. Then you need to train your convolution net. Then you need to train your bounding box regressors. Okay. I guess you need to train your SVM also, right? Okay. So there's a lot of training involved in here, and essence, and RCNN obviously is it's quite slow. Okay, training takes about 84 hours. Takes about this space. I read somewhere it took about 200 gigabytes of this space. Okay, inference is slow. It takes 47 seconds to infer. Okay, and then we have an interlude here. RCNN was a solution. Then something called SPPNet came out to fix some of the issues of RCNN. SPPNet is spatial pyramid pooling. Now, spatial pyramid pooling is, okay, let me go back now. Let me go back this way. Okay, you notice that RCNN actually does a lot of this stuff here. Like you got 2,000 RI, you got 2,000 of this convolution. Spatial pyramid pooling doesn't even do any of this. Spatial pyramid pooling actually just does it once. And then after it does once, it pulls all the it pulls all the features together, okay, into a feature pooling layer of some sort. And then it actually implements the ROI on the feature layer itself. So after that, I think Gershwin got the hint, and he came out with fast RCNN. In fast RCNN, goes to the same thing. Same thing as SPPNet. Through the convolution once, then you actually take the regions of interest. Regions of interest are actually projected onto the 5 feature map of the image. Then all those different ROIs are warped into a ROI pooling layer. Not warped, sorry, they're summarized into a ROI pooling layer. It's a pooling algorithm, it's not warped. After which they feed into a fully connected layer, sorry. They develop where they go into the softmax, which is the softmax classifier, and then bounding box regressor. Okay. The difference between this and RCNN is basically this is a single, all the image information goes to the convolution net once. Whereas if you have 2,000 ROIs, RCNN will push it through 2,000 times. So obviously you're going to get a lot of a lot faster. It will obviously be a lot faster than in RCNN. Okay.
So can I say that the fast RCNN, the big difference is that you're doing the region of interest calculation after the convolution?
Yes.
Layer. So you
The output
recognize feature map. So you only do the convolution once.
Yes.
You do it at layer 5, right? That's why it's called
Yes, code 5.
So you have a
5 and
set
then
of layers that come out of the convolution, and then you do your region of interest proposal there.
yes.
And is there any reason why did they say in the papers or in the lecture whether why they're using L1 loss versus L2 loss? Because in the previous one that you guys were talking about, it was L2 loss for the bounding box, but now it's become L1 for that.
I think during the lecture, he said that the loss you use for the classification can case by case basis. It depends on the problem that you're solving.
Sure.
It could be L1, it could be L2, it could be smooth. I mean, these are some of the hyperparameter that you can cross-relate it to see that which one suits your data set most.
Okay. Yeah. So they didn't give a specific justification.
Yeah. Somebody asked during the class, but I said that this depends on case to case or data set to data set. Yeah.
I think it's just like the stirring the pot. You keep, I guess they probably got better results with L1 loss. Smooth L1 loss.
In the paper, it said that the smooth L1 loss is less sensitive to outliers than L2. That's just what the paper said.
Why would they have outliers in their data?
I don't know.
Anyone
I haven't read the
guess?
paper.
I think the region of proposal is there's a lot of noise.
That seems to make sense. Like not all of your regions are going to be actually good. Some of them may be outliers. I can buy that. So for the fast RNN, after the fully connected layers, you have a bunch of regions, right? Each region, like there's 3 regions here, and each one is being labeled with a particular classifier as a particular class.
No, they have to go through the fully connected layers first, and then based on their output, they are classified or they regress.
Okay.
So that's actually done on the output from Conf5, the process output from Conf5, as opposed to each coming right up to the network.
I'm still having a little bit of trouble understanding what is coming out of the FC layer. Right? You've written linear plus softmax. I guess that's to decide which patch has what label.
Yeah.
And then the linear part is the regressor box, right?
Yes.
But how do you get multiple outputs out of that? You would need multiple outputs, right? Because for each image, there could be multiple bounding boxes that correspond to multiple images.
Okay, the iteration carries on. So if you got 2,000 of these boxes here, each of this is a separate iteration.
Oh, okay.
So that's the key part. We've eliminated the 2,000 iteration from the conf-net, but it's basically still here. Okay, and that's where I guess the hard part is faster RCN. Faster RCN actually. Okay, before I go to faster RCN, is that okay? You notice that all those previously the iterations are still there, whatever the case. So you have 2,000 iterations here. So somewhere along the line, okay, another group of people came up with something called multi-box detections. Okay, and in a multi-box detection, they actually propose a regional proposal network that can actually be trained to detect, to propose all these parts here. So Fast RCN was born using that concept, where they actually have a separate or they have a small what do you call it, network that actually proposes the regions of interest. Okay, this is the part that really gets. Okay, the difference in timing is substantial. As you can see, the fast RCN, okay, this RCNN and this SPPNet. So the benefit that SPPNet actually just went once through Convolution net, brought down the amount of time almost by more than a tenth. Okay, so but the difficulty with, I mean, there are a few disadvantages of SPPNet, but the thing is, when they implemented the same fast RCN, then this became faster again. So this is a process of evolving by using different things to reduce basically the calculation of the RPN. Okay, this part gets a bit heavy as well. Okay, faster RCNN. Okay, this is the region proposed. Now you notice there's no more calculation of RPN. RPN is actually coming from this network itself. So in this network, it actually calculates RPM by processing plus these two quantities, and then giving this proposal is channeled into the final layer, which will calculate the classification loss and the multi-box regression. Okay, the key here is, of course, the RPN here, which is, as I said before, is trained to recognize region proposals. So there's no longer any need for a separate RPN algorithm. And these are the separate test types. You can see the faster CNN is quantum improvement over speed. This is not even registerable in the overall scheme of things. Okay, questions?
How does the CNN propose region? Did they say how?
Quite complicated.
You guys want to go over that, or you're happy with the level of detail? Want to go over it?
No, from what I see from the lecture, right? Can you go back to the slide? 81. So the first, for the proposal classification loss is a binary classification, whether the box is an object or not. So that's to determine whether that box is useful.
The lecture says binary, but it's not really binary. What actually happens is that it creates something called an anchor, okay, which really transforms the image into 9 different variations, and then they try to predict all the k possibilities, you know, at one time. And then what they do is they, from these k possibilities, they grab the best. I guess they grab the best few ones, and then they send it out forward as a RPN, as a proposed region. So I don't think it's, I mean, from what I read, I didn't get it. I didn't get any binary yes or no.
It's a cross entropy, which can cater for multi-class. Cross entropy.
Yeah. What I did get out of it is that for every single potential proposal, they actually calculate all the classes one shot. So it's a multi-class calculation, but how they choose it, what they choose it, maybe is probably another hyperparameter. Because at this point in time, if you started in 2000, you get around that also. So part of this this regional proposal level is to actually fix how many possible predictions you can get per box.
So can I paraphrase them? You're saying that for each region, how they do it is they push it all the way through the softmax, and then you're getting a prediction of all K classes, right? And you're choosing, if it was determined as, let's say, a car, then that's filtering back all the way through the back prop to say, yes, this region was actually something,
yeah.
Right? It doesn't matter what type of object it is, but was something of interest. So when that gets back propagated, the region proposer will know, okay, that was actually something. So I count it as a positive class,
yeah.
Right? So it didn't matter whether it was a cat, a car, a piece of sky, or something, but as long as that region was proposed as something.
Yes, those boxes, these boxes proposal are essentially okay. The bounding box proposal is essentially class agnostic, they call it. Right. But the classification, I'm not sure how that fits in together. But both together, they will actually develop into proposals which they'll set up to this royal cooling area.
Okay. Any questions? The more questions, the more discussion we can have. It's not that clear to me, but if it's clear to you, that's great.
Yeah, the standard guy used the word heavy twice about this. Yeah, he said this part here is a bit heavy.
Okay. Lots of technical stuff.
I'm not sure when they train, right? Do they train the negative cases as well? Because they obviously have a set of bounding box for the picture, right? But do they input in, let's say, this is a bounding box and this is not a bounding box. So do they fit in?
So among the K classes, there's one more class called background. If there's no object in that bounding box, it's classified as background object.
So how do they, when they train, how do they put in the coordinates of the background, because it can be many?
So I think in the training image itself, it has some ground truth. So it says that this pixel belongs to a certain class or this pixel belongs to the background. So let's say your original interest is capturing this one, and the highest probability that it is a background object. If your bounding box, if your ground truth bounding box doesn't have anything in there, then you have a heat, right? Something like that.
But there's a good point. I mean, like potentially there are exponentially many negative sample bounding boxes. Like you can draw an arbitrary rectangle, and probably that's going to be not a bounding box, right? So even if your softmax classifier says, I don't know what this is, I guess the most likely thing is going to be background, and it's a negative sample, right? But I guess the question is, if you have so many potential negative examples, right? Which ones are you going to use as actual negative examples to train the classifier? Because if you send every possible negative example, then you have too many, right? You have way too many negative examples to overload.
Yes, I understand what you say, but like Daniel say, the Justin didn't really go through this one, but I think when answering the question he mentioned about it, you can set a certain rule such that if your bounding box in the overlapping, there's a certain percentage that it belongs to a non-background pixel, then you have a heat. It doesn't cross the threshold, you classify as background. That sort of stuff. I think perhaps there are some classifiers. I said this threshold is something another parameter that I use to do whether it's a background object or non-background object.
I think there's also some of the algorithm that actually says which is a negative. What's not quite negative? Which can be used as grounded, which cannot be used as grounded, which negative. I forgot the terminology, but is the definition of what cannot be used is based also on whether this box actually, I mean, this was compared to the ground truth box, right? So whether these boxes are actually similar to the ground truth box based on IOU, intersection over union. Okay, so they have some parameters. If it's 50% overlap and it's okay, then it's okay. If it's more than that, it's not. It's okay. It's not okay. So they select or they reject positive truths. Is it say that based on some of these IOU criteria. So they filter a lot of that away, and then but it still ends up with quite a number of them, and then they use those as potential proposals to here. Then even up here also, even up here at the bounding box also, there's a lot of you may have many boxes around a particular image. For example, what are these actually? What are these? For example, this. Okay, so the bounding, right at the end of everything, you still need to take care of all these boxes. So that's where they do the bounding box regression with non-maximal suppression. Okay. So I mean, you got a dog here, right? And the cat, but this part of dog, but so is.
It's subsumed in the bigger example.
Yeah. So they have to. The final stage is still to suppress the non-maxima. And then you end up with, hopefully you end up with with more centered boxes.
So you say non-maximal suppression, you're basically saying what is the largest bounding box, right?
Yeah.
That contains the label with a certain amount of certainty.
Yeah.
Okay. So you would discard all the small boxes here in favor of the two large ones. One that says cat, one that says dog.
I think that's what the algorithm does. At least what I read about it anyway.
And you would accept both regions because the amount of overlap is not too high.
Oops. Oh.
Hello, my name is Remy. I'm a first year PhD student. So the problem with Daniel has talked about three algorithms: RCNN, fast RCNN, and faster RCNN. They are called the region-based method because you need a region proportional network, right? But the problem is this is about the faster RCNN is about 200 milliseconds, which is when converted to a frame per second is about 7 frames per second. So it's still not good for a real-time application. For example, if you use it for autonomous driving car, or maybe you want to put your object detection in CCTV or embedded system, this is still not good enough. The problem is that they have so they kind of split the network into two parts, right? The main idea is why don't we club it together into one network to make it faster? And there is the main idea of these two network. It's called YOLO. This is not you only live once, but you only look once. This is called you only look once because you only look at the image once and then you apply convolution directly to get the output. And the second one is SSD. This is single shot detector. So if it's the same idea, is single shot. You can get the object in a single shot. So the main idea is that we kind of club these two together. So we just change our network into a big regression network. So the output, so given this input image, the output is just a 3D tensor. I will explain it later. So the method is first we divide the image into a grid, 7 by 7, for example, in this part. And then in each grid we create some kind of base boxes centered at each grid cell. Here B is equals to 3, so you have this tall box and the white box and the square box. Later we will some kind of repair this box to get the object. So within each grid cell, we need to predict basically 5 numbers. This is the regression part. So we need to predict the x, the position of the x and y, the center dot, and then the h and the w, which is the height and the width of the box, and then the confidence, which is the probability whether there is an object in the box or not. And then within each grid cell, we need to predict the score for each classes, including background. So finally, the output is 7 by 7 by 7 by 7 is the grid by 5 by b, because for each bounding box we need to predict 5 regression number, and then plus c. For each grid cell we need to predict c. So basically, in this box, whether this is probability of a background or a dog or something, in this grid, whether the probability of dogs should be high. So we kind of make like a class map for this image. So what is the difference between YOLO and SSD? So they are kind of fighting each other to get the best result. So YOLO is, so SSD is much faster. So YOLO create the first version called YOLO version 1. It can run on NVIDIA Titan X GPU or something with 45 FPS. So when it's converted to time, it's kind of 0.02 seconds, so only 20 milliseconds. And then SSD proposed a new network, and it can run faster and with a higher accuracy, because they add more tricks to the network, like image segmentation, and they add more features, something like that. Maybe I can show you the. So the code is available on GitHub. You can download it if you want, and you can use it in your own GPU. Okay, so this is the example of YOLO run on a video of YOLO run on James Bond film. You can see, maybe it's not. You can see the text person. Maybe I need to screen. Chair, umbrella. Chair, car, and something like that. So this is trained on a dataset called Pascal VOC. It consists of 20 class, like person, cell phone, motorbike, car, and something like that. Tires. So and then YOLO create a new version, which is YOLO version 2, which is shown here. And as you can see here, so they get the higher precision MIP 76.8 with 76 FPS. So it is faster, and I think this is currently the state of the art for object detection in real time. And then the next problem with object detection is there is a lot of variables to taken care of. For example, the base network. So for faster RCNN, I think they use ResNet, right? ResNet, I think. And for YOLO, they use some kind of modification of GoogleNet. And for SSD, they use VDD16. So you can try to different base network to get a different result. And then the next thing is we need to determine the object detection architecture, whether to use faster RCNN or SSD or YOLO. And this one is RFCN, is kind of a hybrid of region-based and SSD. It's a region fully convolutional network. And then we need to determine a lot of hyperparameters like image size. So for example, here I think they shown it. Yeah, for YOLO it's 544 times 444. SSD 300 means the input image is 300 by 300. SSD 500 is 500 by 500. And so if you want to see some kind of experiments that do this comparatively, you can look at this paper. It's a speed accuracy trade-off for modern convolution object. This is a good paper that try to experiment with a lot of these hyperparameters. And the main takeaways is there is no free lunch theorem, as in there's no better algorithms, the best algorithm for object detection. So for region-based, the conclusion is slower, but more accurate. So if your application is, time is of essence for your application, then you should use SSD or YOLO. But the trade-off is not as accurate as using region-based method. And last week we talked about the image captioning in RNN, right? So image captioning is a problem where you get an input of an image, and the output is the captioning of the description of the image. But the problem is that for image captioning, you only describe the whole image. Now you want to combine this object detection and captioning, and it is called dense captioning. So you want to caption each of the object in the image. For example, red shirt on a man with black hair, floor is brown, something like that. And this is the work of the lecturer Johnson and Feifeli. So the main idea is that it is basically same as faster RCNN. So you get the image here. They use, I think, ResNet to get the convolution features. And then they use this is almost the same as faster RCNN. You get the region proposal, and then you select the best proposal. And then you get the region features for each ROI. So B here is the number of bounding box or the ROIs. And then after you get the features for each ROIs, you put it into a recognition network, and then you get some codes. So B times D is the dimension of the code. And then you put it on the LSTM for each B, put it on LSTM to get the description of the object. This is an example. Okay, as you can see here, is describing the whole image, the whole videos. You can see man with a bird. So when this is Andre Carpati, by the way, and when they put glass in his clothes, it said that white logo on the shirt, so they cannot detect. Then when he pick up the mouse pad, it say a brown and red teddy bear. It's actually a cat, kind of a cat. And here they see again. So here is when they don't understand what is the image in this whiteboard, they say picture of an unknown. So this unknown is some kind of like a unique. So in previous week on RNN, they have start tag and end tag, right? For unknown, they usually use this unknown tag. So they cannot describe the picture. And there is a white microwave on the wall. Man wearing glasses. Door is open. Copy or something. And this is Justin Johnson. So how do you train this network? So there is an available dataset called the there is a dataset that describes all of the image with the visual genome dataset. So you can use this training. So all of this problem are supervised. It's not unsupervised. So because we have a lot of training data, we can just design a network and then just get the promising result with CNN and deep learning. Okay, there is object detection. Now we move to the last part of the computer vision problem, which is the instance segmentation. So instance segmentation is kind of like a hybrid of this segmentation, this part segmentation and the object detection. In semantic segmentation, you see when there is two cow, there is two cow, it doesn't separate the two cow, right? Okay, leave it. It's too far. Yeah, it's way far. So when you have two cow in an image, which is side by side, like this one, so it will classify it will segment it as one dog. not a separate doc. So there is in this segmentation, semantic segmentation. But in object detection, we can separate two docs separately. So instance segmentation is the kind of combination of both. So you want the perfect pixel, which is the dog and the cat, and then you can separate the two dogs, not one dog.
So up to this point, I think, I summarize, we're looking at images all separate from each other. Right?
Yes.
So even though if you have a video stream or something like that, each image is being considered completely separately.
Yes.
Okay, so there's no constraints or continuity
Mhm.
that's being enforced. Secondly, because there's no spatial representation, you're not using any model of the way things can actually be presented in the real world, right? So it's not that you can have a cat flying in the air normally, right?
Yeah.
But the algorithms we're looking at don't have any constraints. They just identify regions of interest spatially in the image that corresponds to the object.
So for instance segmentation, the researcher used what is called the mass RCNN. So basically, the idea is simple. It's just a faster RCNN. So previously, we see in faster RCNN you have two separate, right, for classification loss and bounding box regression loss. So in mass RCNN, you just add new output, which is to classify. So this one is the usual faster RCNN. So you add a new branch. Basically, you add a new branch with convolution. Then you predict a mass of each of C classes. So basically, this only predicts given a bounding box. You predict is a binary prediction whether this is an object or not an object. Yeah, that is the idea of mass RCNN, and it also gave a very good result. So, for example, this you can see they can predict two separate motorcycles in a person, and if you can see on the back there are small peoples here, but it can also be classified with mass RCNN. And previously, Xiaomei also talk about joint post estimation, right? So mass RCNN also does post estimation. The idea is also simple. In faster RCNN, you just add new output. Basically, you add new output to predict the joint coordinates, which is a regression problem. And this is the output. So given an image, you can predict the number of person and the joint separately. And so this was trained on, there's also a big data set by Microsoft called the COCO dataset. So it was trained on, I think, 90 or something of class object categories, and and it consists about 300,000. So for example, if you want to choose banana and cell phone, for example, you can search. Some kind of market with the cell phone is, oh, it's very small. Cell phone is here, and the banana is here. So it is annotated by Microsoft, so you can use it. This is the banana, the cell phone is there. So again, this is all supervised test. You have a lot of data, you just create your own architecture and then you train it using CNN. So to recap, we have talked about 4 computer vision problem besides image classification. We have talked about semantic segmentation, classification, classification, localization, object detection, and last is instance segmentation. Okay, that's it. Any questions?
So we have 30 minutes time for questions because our nice friends who dropped by our class are coming at 8 o'clock. So that is our recent friends who have been using CNN since day one. As you know, they've reached, I think, Series B funding, so there was quite a lot of money. So definitely, I think we want to stick around and hear what they have to say about research. And we can ask them all the hard questions because obviously they've done all of this stuff too. So we can ask them, how do you come up with negative examples? What type of, when you've done any work on MS, CNN, like that. Questions from the floor, all of you guys. So I think there was a post by Jeffro, right? Did you make a post on the slide? Yeah. So I'm looking through that while the slides are going up, and I think that's really nice. Maybe you could put up that blog post up on the computer. Walk through that so that we can have a complementary narration against what we've just heard on the slides. Can you do that? I'm not saying that you guys have to narrate, okay? If you guys don't want to narrate, I won't narrate. It's okay. So really, this is supposed to be a nice discussion class. It says I don't think any of us are that well versed with the literature, and the literature is coming out as we speak, literally. So it's more fun to stay more real time and have all of our GPU brains working on the problem of understanding what other people are doing. This one, right? So you guys have it on Slack, so you can pull it up with us. So I guess this is the mass CNN paper, RCNN. And so they cover pretty much the same things as what we just talked about in the lecture, right? RCNN, fast CNN, faster CNN, and mass RCNN. So they give a more narrative version of this, right? So they said that Hinton's lab came out with the original RCNN proposal, and then they wanted to see what it generalized, and then understand what that is doing. So as we've already talked about, the RCNN approach is sort of like brute force, right? We just take an image and we propose everything coming from a simple, low-cost region proposal system, which is doing something like what this is doing over here, which is like some blob detection, right? So saying all the stuff in this region is of the same type or texture or color, and so I'm going to propose that as a blob. And then I'm going to give you the bounding box around that, and I'm going to ask the CNN to tell me what it is, right?
The specifics for that are the link right below.
This one?
You can read about here.
Okay. So if you guys like, we can, because we have some time, we've got 20 minutes or so, we can actually try to read all of these papers at a very high level. I like to propose this to my PhD students. So if you're a research student, you should also practice this, okay? Is basically just spend 5 minutes with each paper that you get and get a sense of what's going on. Because that will allow you to read, something like 50 papers a day, which is great because that means you can actually stay sort of like up to date, right? So how do you do that, right? Basically, when you read papers, you shouldn't be actually reading them. You should be skimming them, right? So your idea is to look for keywords that are useful for you. And often what I teach my research students is you look for certain components, like you're looking for methods, you're looking for data sets, you're looking for shortcomings that can generate future work that you could do. And you're looking for, what else? Metrics, yeah. Metrics that you're using for evaluation. So even when in my own work, I do a lot of digital library work on scholarly papers. So I actually like to train machine learning algorithms to do exactly what I just told you to do,
which is to detect data sets, detect evaluation measures, detect methods. So we can write systems that could summarize that. Imagine if you said something like, what's the current state of the art on neural networks for vision? And then, you know, the computer spits back at you a list of 50 papers, which data set they use, what's their F1 detection for each one, you know, what are bounding, what's the runtime for each one. And you could actually do that if you could get all this stuff extracted, right? So that's the goal of some of the research in my lab. But anyways, what we can do is try to do that. So when I read a paper, I just generally read the abstract. So it's looking at selective search, diversification. I usually don't care about numbers so much. You know, they have a data set and a software that's available. And then I won't really look at much here. So for example, for this paper, the first thing after I read the abstract is I'll read the final part, which is like the conclusions, right? That summarizes what they've done. And also if they have a future work section, some of them do, then you can read that as a good way of getting an idea of what's going on, right? The other thing you can do is you can try to read related work. I think that's very helpful to give you an example very quickly about where that piece of literature lies. So they say that exhaustive search is something important to them and segmentation is important to them. So even within 30 seconds to a minute, you already have pretty much squarely put this paper in that case where segmentation is one of the possible goals, and you know that they're using some exhaustive method, right? So they tell you exhaustive search, segmentation, and sampling strategies. Okay. So what can we get out of this method? So do you guys all know what the selective search algorithm does? Why they do that? Can anyone summarize?
From what I know about selective search, it's based on this guy called Dodson swap algorithm. What it does is it uses an undirected graph for the image, and then based on a sequence of similarity measures, it will actually segment the graph into different segments. Then it does a greedy algorithm of all the segments and merges those that are most similar. After all that, it does regression on the segments, on the individual segments that have whether it's previously segmented or merged together. They're all it generates a bounding box for that.
So I think one of the other things that's useful about the selective search algorithm is it has to be very efficient, has to be very fast, right? Because you're running this possibly many times to get output. So this set of slides that this blog post has linked to has talked about the effectiveness in terms of accuracy, right? And then what types of features went into that. Things, yeah, okay. The vSense folks are here. You can let them in. So we can come back to this later if you guys want. I think I didn't know about this data set. This looks really fun. I'm gonna have to try that. I didn't know bananas were co-located with cell phones, but at least it happens in 28 examples. That's really awesome. Okay, so we'd like to first welcome Todd and Guangda to our class. So Guangda is the CEO of vSense, the startup that we were mentioning that comes out of NUS from Prof. Chua Tat-Seng's lab. And Todd is formerly a PhD student in the graphics group and is now an employee at the first rank for the machine learning side. So do you guys want to come up and present?
Have you finished?
Yeah, we're just actually going through this lecture's work. So we were looking at fast RCNNs and mass CNNs.
Continue. I also borrow the vocabulary.
Okay, well, we're just going through some of the papers. I think you probably read this blog post, right? This one. So April 23rd. So it's at least, what, 4 months old? So probably you've seen it. So they were going over RCNN to mass CNN, these 4 papers, which I guess you've read or know of. And the lecture that we went over was, where is it? Here. This is Fei Li's lecture notes for, oh, how do I go all the way back? I don't even know how to use this tool. Where they're going over detection segmentation. I think the group is more interested to hear from you than me. So why don't we break for a little while and let them introduce their company and say something about the technology that they're using. And then after that, if you guys want to stay around, we can continue going through the blog post. How's that? Would that make a lot of sense? Okay. Yeah. Why don't we do that? So do you have anything you want us to point to, or
Yeah.
come up and you're going to show your own stuff?
Yeah.
Okay, great. So I'll take out the projector here.
You want to have a break or?
No, we're good. So the class is on YouTube. We broadcast every week.
Really?
So do you want me to point to the projector so that they can be recorded, or you don't want it recorded? It's also fine.
I think I would prefer not to be recorded.
Okay. Okay, so we'll end the video part of the class.